This is session 26 of Information Security. The course code is CS413 and our today's topic is LZW technique. It is a compression technique and we will see how to compress any string using LZW today. First, let's talk about extended ASCII table. We have entries from 1 to 255 in extended ASCII table, where we have symbols, special characters, upper and lower case alphabets, numeric values, etc. We will require this extended ASCII table for preparation of dictionary in LZW. So this is our string. The rain in Spain falls mainly on the plain, along with the slash. We have to create 5 columns. First column is that of character that we are reading, and then we will create a string using the previous character and the present character. Then we will look in our table, and the table is the extended ASCII table, whether that entry exists or not. The fourth column is the output. We will output the previous character, and finally the new entries will be added to the table. So let's see how to process the given string. First, we are going to read the character T. Since it is the first character, we won't be able to form a string using the previous value. So for the first character, there are no entries in the table, nor there is any output or addition to the table, because a small t already exists in the extended ASCII table. After t, we are going to read h. A string will be formed using this present value and the previous one. So our string becomes th. Then we will look into our table. Again, I've told you that this table is extended ASCII table. Definitely you will never find th in the table. So our answer is no. We will output the previous character, which is t, and we will add to table this new string th. Since we have values 1 to 255 in extended ASCII table, this new entry will go at the position 256. After h, we are going to read e, and the new string will be he. This he exists in the table or not? The answer is no, and we are going to output the previous character. This he will be placed in the table at position 257. After e, we will read slash. So the string will become e slash. E slash is not in the table. We will output e, and this e slash will occupy position 258. After slash, the next character is r. A string will become /r. We will take the previous character and the present one. We will look in the table. The answer is no. /r does not exist in the table. So the output will be slash, and this entry, the string /r, will be placed at position 259. After R, we will read A, and our string will become RA. Again, this entry is not in the table. We will output R, and RA will be added to the table at position 260. This process will continue. Now we are reading character I, and our string is /I. We will look in the table whether it exists or not. Our answer is no. The output will be slash, and /I will be added to the table at position 264. After I, we will encounter N, and the string will become IN. We'll see whether this value exists in our table or not. The answer is yes. It is at the position 262. Whenever this happens, and the answer to the question whether a string exists in the table is yes, we will not output anything, nor will add anything to the table. And the reason is that in already exists in the table. After this point onwards, we'll see whether this string, after joining with the next character, is present in the table or not. So we will join in this time with slash, and we'll look in the table again. This time the answer is no. In slash does not exist in the table. In that case, we will output the previous yes value, which is 262. And in slash will be added at position 265. The next value is S, and it will form a string with slash, that is the previous character. So the new string is /s. It is not there in the table, so we are going to output slash, and /s will be added at position 266. After S, we have P, and the string becomes SP. It is not there in the table. Output will be S, and SP will be added at position 262. Again, this process will continue, and then we will encounter I of Spain, right? So at this particular point, I will form a string with A, that is AI. AI exists in the table at position 261. So we will not output anything, and nothing will be added to the table. Then in the next step, we will join this AI with the next character N, and our new string will become AIN. And then we'll see again in the table whether AIN exists or not. Answer is no. So in that case, we will output the previous yes value, which is 261 in our case, and AIN will be placed in the table at position 269. Right after that, we will encounter slash, So the last character was n and the present is slash. The new string will become n slash. We will check whether n slash exists in our new formulated table or not. The answer is yes at position 263. Like always, there will be no output and no addition to the table. This particular string will be concatenated with the next character, which is f, and the string will become n slash f. Now this entry will be checked in the table. Answer is no, it does not exist there. So we're going to output the last yes value, which is 263 in our case, and n slash f will be added at position 270. We will continue with the same process for A, double L, S and slash. Now till now we have successfully processed the string from the rain in this pane falls slash. Now we will start from M, that is the first character of mainly. So we are going to read this character M and we will concatenate it with the previous value or join it with the previous value to form a string slash M. We'll do what we are doing till now. We'll check in the table for its existence and the answer is no. Output will be slash and this slash M will be added to table at position 276. The next character is A, which we will join with the previous character. So our new string will become MA. We will look in the table for its existence and the answer is no. Output will be M and MA will be placed at position 277. After A, I will be read and the new string will become AI, and this AI exists in the table at position 261. So whenever something exists in the table, the output is nothing and nor we are going to add anything to the table. We will move forward with this string AI and join it with the next character. So the next character is N. Our new string will become AIN. Again, this AIN exists in the table at position 269, so there will be no output nor any addition to the table. We will continue with this string to see whether the next new string is in the table or not. So the new string is AINL and we will check in the table. No, it does not exist, and whenever this happens we will output the last yes value. In our case that is 269, and we will add to table this new string which is AINL. Now after AINL we will continue the same process till the end, traversing each and every character and compressing it. As you can see, the final thing is end of file and the slash will be output. The final value in the table will be AIN slash at position 288. I hope you're going to try this yourself. After doing so, you will do this computation yourself and you have to count the total number of characters in the input along with the slash everything. Even if there are numbers you have to count them, and in our case the total characters are 44 multiplied by 8 because every character has 8 bits, we'll get 252 bits. It means that the string contains total 352 bits. After compression, this will become 306 bits. How? You will take the output value, you will count them, and in our case, this value is 34, but we are multiplying this with 9. Why we are multiplying this with 9? Why 9 bits? Why not 8 bits? The answer is that since we have new values at position 256 onwards, then naturally we cannot represent those values with 8 bits. In 8 bits, if we turn every bit on or 1, the value is 255 maximum. So how can we represent a value 262, 263 or even 256? For that, we need to represent every character with 9 bits. But even after doing that, the final result is 306 bits, which is less than the initial value, 352. So at input we had 352 bits and the output has 306 bits, which is a difference of 46 bits, or we can say that there is a compression of 46 bits. This was LZW technique, where we compressed a given string, and it is always difficult to select this sort of string where there is a possibility of compression. Otherwise, compression is usually for huge data. I want you guys to practice this at home and take different sorts of string and see if you can compress them or not. All the best.